So as people are slowly getting in, let me just write down the three cases we did yesterday. 2.3. I'll write it here so that the projector won't block the view on that side when I lift it up. So section 2.3, that was what we did yesterday. Okay. We were doing homogeneous constant coefficient linear second order, because that's a long title. Okay. So constant coefficient second order linear homogeneous differential equations. A is not equal to 0, B, C could be 0 if you want. And the characteristic equation is the quadratic equation AR square plus BR plus C equal to 0. That's because we know that the solution is of the form y equal to e to the power of Rx. And then if you plug it into this equation, you get the corresponding characteristic of the auxiliary equation. Okay. And the roots are given by negative b plus or minus square root of b square minus 4ac over 2a. You could solve this in most cases without using this quadratic formula. That depends on the kind of problem you have. Okay. And then depending on the sign of this radical here, you could write three different cases. Case 1, if b square is strictly greater than 4ac, we have two roots, R1 and R2, which are not equal to each other. Both of them are real. And you could write the solution as y of x equal to c1 e to the power of r1x plus c2 e to the power of r2x, where c1 and c2 are constants that you could calculate based on the initial values given to you. Case 2, if b square is equal to 4ac, that is when you have two real roots which are the same. Okay, r1 is equal to r2. In that case, you have y of x equal to c1 e to the power of r1x plus c2 x e to the power of r1x. Okay, r1 and r2 are the same, so there is no meaning in writing r2 here. Okay. And case 3 is when b square is less than 4ac. So you have two imaginary roots, p plus or minus iq. Okay, so r equal to p plus or minus iq. P is the real part, q is the imaginary part of that set of roots, and the general solution in that case would be e to the power of px times c1 cosine of qx plus c2 sine of qx. So the first solution is purely exponential. Okay, depending on R1 and R2, it could be exponential growth or decay. The second one is also exponential, but this x term is going to create some problems there. Might slow down or speed up the exponential growth or decay there correspondingly. Okay. And this one is exponential and oscillatory. If p is equal to 0, it is just purely oscillation. But if p is not equal to 0, and if it is positive, it's going to be oscillations that grow with time. P is negative, it's oscillations that decay with time. We did a bunch of examples yesterday, so I hope all of you are comfortable with this, which is what we are going to use in today's application. So I will leave it there for today's discussions because we don't have to then keep looking back into our notes about which case is what. Okay. All right. I think more people are here now. Let's move on to section 2.4. Do you have any questions before we start? Don't forget about test number 1 on Thursday. That covers chapter 1. Okay. Keep that in mind. Yeah. All right. All right. Let's move on to section 2.4. Free mechanical vibrations. So it's going to be an application of what we did in 2.3. Okay. So it's an application of the kind of second order equations we were discussing yesterday. Okay. So this is the setup here. We have got a spring and we have got a mass. Okay. Spring is suspended from some kind of a support. So this mass is m, could be in kilograms or pounds, depending on your choice of units. Okay. The property of the spring essentially is to resist whatever you do to it. Okay. If you push it up, it's going to restore itself downwards. If you pull it down, it's going to restore itself by pulling up. Okay. So there is a measure of how that spring behaves for each force that you apply to it. And that measurement is given in terms of a constant K. So K is called the spring constant. So it's the amount of force you need to apply to either stretch or compress the spring by 1 unit. Force to stretch or compress the spring by 1 unit. When it's a 1 unit, it could be 1 inch or 1 centimeter or 1 mile, okay, depending on your choice of units. Now, if you just, assuming that there is nothing else going on here, if you just pull this and let go, it'll just start going up and down. Okay. That's what it'll do. So we need some kind of a mechanism to stop that vibration at some point or the oscillation at some point. Okay. So we'll keep some kind of a block here. Okay. Usually we denote it like this so that it looks like it's going to stop it from oscillating too much. This is what we call as a dampener. Also called a dashpot. Okay. So the purpose of the dashpot is to reduce the amount of oscillations and bring it to stop at some point. So this dashpot also has some kind of a constant called the damping coefficient C. Okay, I'll talk about that in a few minutes. So this equation is usually given in terms of these 3 letters, okay, M, C, and K. M is the mass, K is the spring constant, and C is the damping coefficient. For the time being, we're going to assume that there is no other external force. So we don't want to start with very complicated problems and then not know what to do with it. Okay, so there is no other external force other than these 3 components. And that is what we mean by free mechanical vibrations. Okay, it's not forced by anything. All right, so let's look at what kind of forces we have on the system. Okay, so the force on the spring is given by what is called as the Hooke's law. So as I mentioned earlier, the spring is always going to do opposite of what you're doing. Okay, so the force on the spring, that's denoted by Fs. Okay. It's going to be equal to, so it's proportional to how much of displacement you create in the spring. Okay, so it's going to be negative of K times X, where X is the displacement given to the spring. Okay, whether you push it up or pull it down, there is some kind of motion with respect to time. Okay, that displacement is denoted by X. from the equilibrium position. Equilibrium in this case means when it is not moving. So x equal to 0 is your equilibrium position. So from there you could either push it up or pull it down, and the resulting thing is what you call as x there. And this negative is because of the restoring nature of the spring. Okay. Which means that if you pull it up, it will come down. If you push it down, it will come up. Okay. So this k is a strictly positive physical constant, always. K cannot be negative. So if you want to find the value of k, you have to take the absolute value of the equation, because if you take the negative sign, the k will come out to be negative. Okay. So k is the absolute value of the force divided by the displacement x. So that is one of the components there. Okay. So we have a mass, we have a spring. So the spring is governed by that force. We also need to look at this dashpot here. So the damping force. In the word dampening means it's going to kind of slowly kill it. Okay. So damping force, let's call it as FC because, or FD because of dashpot. It's proportional to how fast it is moving. Okay, so the faster it moves, the faster it's going to kill it. Okay, so it's proportional to the velocity, or in other words, FD is equal to negative c times the velocity v. It's negative because it's going to reduce the oscillations. Again, c is a strictly positive quantity here. Okay, this is very important because you shouldn't be looking at these equations with negative coefficients ever. Okay. K is a positive number. M, of course, is positive. It's a mass. Okay, that goes without saying that M is greater than 0. So all these are strictly positive numbers, and the negative sign is already in the force, which is because of the opposite nature of the behavior. Okay. All right, so let's write Newton's second law of motion here. Which tells you that the total force is equal to mass times acceleration. Okay. So we are given the mass here. So we have mass times acceleration is equal to the force due to spring plus the force due to the dashpot. These are the only two forces here. The net force must be equal to mass times acceleration according to Newton's law. So let's write down what we have here. Fs is negative k times x and Fd is negative c times v. So Ma equal to negative kx minus c times v. That is not a very useful equation because it's got too many things going on there. Okay, but we know from calculus that the velocity is the first derivative of the displacement, okay, dx dt, and acceleration is the second derivative of displacement, d square x dt square, where t is a time. Okay. So there is a small adjustment of notations here. Yesterday we were doing everything in terms of y and x. Okay, now you're doing x in terms of t. So you'll see the small annoying change of letters between 2.3 and 2.4, again between 2.5 and 2.6. Okay. I don't mind if you do y in terms of x for the spring mass problem, but it looks awkward if you talk about time as x. What is your choice? Okay. All right, so this becomes m times d square x dt square equal to negative kx minus c times dx dt. Okay, so now you can see a second order linear constant coefficient differential equation slowly evolving out of this. Okay. Bring all these terms to the left hand side and it becomes homogeneous. So this becomes mx double prime plus cx prime plus kx equal to 0. So the only difference between what I've written here in this column here and this equation is that my variables are x and t instead of y and x, but it's the same properties of solutions that we're doing. Okay. So once again, m is not equal to 0 and should be positive. Okay. C could be equal to 0. I'll talk about it soon. So C is greater than 0. K also cannot be equal to 0 because if K is equal to 0, there is no spring. Okay. And should be positive. The reason why I did not write C not equal to 0 is because we could look at a case where there is no dashpot and see what happens. Okay. So that's what we're going to focus on today. So we will look at how the system behaves in different situations of mass, dashpot, and spring constant, and what kind of behaviors we expect out of this. All right, any questions about any of that physics stuff? Some of you would have already seen some of this in your physics 1 or other mechanical engineering courses, okay, but the basics are the same. All right, then let's then look at the easiest case. Okay, let's start with the case where there is no dashpot. So let's assume that this thing is not there. So case 1, C equal to 0, okay, no dashpot, which means it's going to be undamped oscillations. Later we'll talk about underdamped oscillations. This is undamped, okay, so don't confuse the two words. Let me ask you this, and we have been around for a while now on this planet. Okay. If without this thing, just the spring and the mass, if I pull this down and let it go, what will happen? It will go up and down and up and down. Will it stop? Yeah, but what is stopping it here? There is no dashpot. So okay, well, no, let's not make it too complicated here. So, if I just let it go and it'll oscillate, okay. Mathematically, it shouldn't stop because there is no dashpot here. But in real life, it stops. Why is it? Yep. Okay. These are all very complicated things. Gravity. There's something else that we are ignoring here. What is that? Air resistance, right? The friction part. So that is what is really, yep. So we are not counting friction in. Without friction, theoretically, it should just keep on moving up and down. Okay, that's what we should expect. So our expectation is just like if you sit on a swing and somebody just push it, there is no air resistance, just go up and down and up and down and up and down. Okay. So our expectation is everlasting oscillations. In reality, it will stop because of friction. Okay. Very sure all of you do your physics 1 problem saying ignore friction, okay, because it's a very complicated phenomenon. All right, so when you set C equal to 0 in our differential equation up there, it becomes mx double prime plus kx equal to 0. Okay. So our differential equation becomes so it's a second order equation still, okay, but the only thing is that the middle coefficient is not there, which actually kind of makes our life easy. Okay, you can divide throughout by m. And we get x double prime plus k over m times x equal to 0. Remember that m cannot be equal to 0. Okay, it's a mass. Let's call this k over m by the letter omega square. Why is it square? Just for aesthetic reasons. Okay. Could call it omega, but then it looks kind of a little clunky. So put it omega square, it looks nicer. Okay. Mathematicians care a lot about appearance, so just for that reason, let's call it omega square. All right, so the differential equation becomes then x double prime plus omega square equal to 0. Okay. X double prime plus omega square x equal to 0. So it's a second order differential equation. You could write the characteristic equation like we did yesterday. This is going to be r square plus omega square equal to 0. Okay. Pretty sure you have probably used the notation of omega even in your physics 1 class, but give some meaning to it pretty soon. So r square equal to negative omega square, r equal to plus or minus I omega. Remember that omega is a positive number, k is positive, m is positive. And based on case number 3, remember that p is equal to 0 there, okay, and q is omega. So you can write the general solution to this as x of t. X is the displacement with respect to time, okay, is equal to c1 cosine of omega t plus c2 sine of omega t, where omega equal to the square root of k over m is called the natural frequency. Frequency is the number of cycles per second, okay, the number of times it vibrates. So if you look at the units here, the units of k would be newtons per meter. This is in kilograms. If you do a unit check here, it will get 1 over second. Okay, it's the number of cycles per second. Okay. So omega is the natural frequency of the spring mass system. It's natural because there is nothing else that is kind of corrupting it. Okay. Once you bring the dashpot back in, it's going to get all messed up. Right now, it's just the spring and the mass. Okay, that is its natural frequency. It's also called a circular frequency because it goes in a unit circle. Okay. And the time period of oscillation would be given by t equal to 2 pi over omega. Okay. This is a mathematical model. When do we know it works? We know it works when we expect something and the same thing happens here. Okay, we expect that our oscillations will be everlasting. Look at this. This is an oscillatory term. This is an oscillatory term. There is nothing that is stopping it. Okay? And that is what agrees with what we were trying to achieve there. There is no friction here, so there is nothing to stop it. This is what we call as a simple harmonic oscillation. This mechanism is sometimes called an harmonic oscillator because of the same reason. Okay. All right, so it's a good application of section 2.3, case 3 with P equal to 0. Okay. So in case you missed that part, this is case 3 with P equal to 0. Okay, and that P equal to 0 is because there is no dashpot here. Once the dashpot comes back, things get a little bit complicated. All right, so this looks pretty nice and straightforward. Okay, there is nothing fancy here. If you have seen this before, I'm hoping that it's kind of brings back the same concepts you have learned in our classes. Okay. Now we could write this solution here. Okay. Right now we have a cosine and a sine. It's more traditional and more useful if you rewrite this in a more kind of application-oriented form. Okay, so I'm going to show what that means. And this is the only part that could be a little bit challenging in this section. So you just need to pay attention to all the details here. Okay. So we want to rewrite the same x of t that you have there, okay, in the form a times cosine of omega t minus phi, where a is the amplitude, I'll show you what amplitude means. Okay. Omega, of course, is the same as the natural frequency of the system, and phi, okay, this is phi or phi, I don't know, some people call it phi, some people call it phi, is the phase angle or the phase shift. It tells you whether the peak of two different waves are at the same time or is it shifted by a certain time. Okay. That is what we call as a phase angle or the phase shift. Some people also call it as a phase lag. So if it is in the same position, it's in phase. If it is off, it's out of phase. So if you don't know what these words mean, amplitude is the height of the wave. So if you're, remember it's a cosine wave. Okay. So this part here is the amplitude. Now the next, remember that this is a function of time. Okay. The next wave might start like here and go this way. So this gap here is what you call as the phase difference or the phase shift. Okay. So this is slightly out of phase here. So same thing happens here and the next wave and so on. So writing it this way gives you some better understanding of the solution instead of writing it as two different functions. So the same function tells you how strong the wave is and also if there is a lag from the fundamental solution here, okay, at t equal to 0. If the next one is kind of shifted off or at the same phase. Now, how do we find this A and omega? How do we find A and phi, not omega? Remember, A is the strength of the wave. Okay? The strength of the wave is built because of the constant C1 and C2. So A is just a superposition of C1 and C2 without worrying about whether it's positive or negative. Okay. So you're kind of adding C1 and C2, but if C1 and C2 are negative, you don't want to worry about what happens. So if you just square it and add it, okay, you'll get a better understanding of how strong it is and take the square root. That is easy. What is not so easy is how do you find phi? Okay, you have to pay attention now. So for this, we'll draw this right angle triangle with phi as the angle there. The opposite side is C2, the adjacent side is C1, so that the hypotenuse is still the same. It's still, by Pythagoras theorem, it's a square root of C1 square plus C2 square. That is the reason for constructing this right angle triangle, so that this is still maintained. From here, you could write cosine of phi, which is the adjacent side over the hypotenuse, that is C1 over A, and sine of phi is the opposite side over hypotenuse, which is C2 over A. From your high school or whenever you first learned your sine cosine relationships. So I'll do some small manipulations to achieve what we are trying to do here. So we'll take that solution, which is x of t equal to C1 cosine of omega t plus C2 sine of omega t. So what I'll do is I'll divide and multiply this by a throughout. Okay, so it's a times C1 over a cosine of omega t plus C2 over a sine of omega t. I can do that because a is just a number. You can multiply and divide the same number throughout the equation. C1 over a, according to this, is cosine of phi, and C2 over a is sine of phi. And you probably have seen this trig identity from your high school, that cosine of a minus b is cosine a cosine b plus sine a sine b. It's a rather weird relationship. It's a positive there and negative there. Okay, some of you would have seen it, some of you may not have. That's okay. Just going to make use of that here, and that's going to become a cosine of omega t minus phi. Okay, so your a is going to be omega t, b is going to be phi. Okay, and that is how we convert this solution into the amplitude phase form. We don't have to know how to derive it, okay, but the reason why this is the same as that is because of this simple manipulation. So in all these problems, you'll be asked to write your solution in the amplitude phase form. Okay, so you need to know how to do this. All right, there is a little bit more trouble ahead of this. Okay, this is not done yet. Note that if C1 and or C2 are negative, that is going to change the sign of this, these two terms here. Okay, the sine phi and or cosine phi will become negative. Why should we worry about it? Then your angle is going to change. Okay. Remember this thing from high school? All positive, sine positive, both are negative. So tangent is positive, cosine is positive. Okay. All means both sine and cosine are positive. Your sine is positive, tangent is positive, which means that both sine and cosine are negative, and here cosine is positive. So depending on where you are, you need to adjust your angle phi. Okay, you cannot just keep the same angle irrespective of whether your C1 and C2 are negative. So case 1, if C1 and C2 are both positive, okay, we are lucky, nothing to do. Then phi would be the tan inverse of C2 over C1, okay, from this right angle triangle, opposite side over adjacent side. So on a perfect day, that's what I would expect and hope for. Okay, but that's not probably going to happen all the time. So case 2, if C1 is positive and C2 is negative. Well, what does that mean? If C1 is positive, that means cosine is positive and sine is negative. I think I should have started with the other case where C1 is negative and C2 is positive, so that I go in that order. Okay. So C2 is positive and C1 is negative. That way sine is positive. So going from quadrant 1 to quadrant 2. So we are in the second quadrant. So phi cannot be less than 90 degrees anymore. We have to bring it to the second quadrant. And the way to do this would be to add a value of pi to it. So phi would be tan inverse C2 over C1 plus pi. Remember that your C1 is negative, so this effectively is a negative number, and you are adding it to 3.14, so you are in the second quadrant. This is a negative number when C1 is negative. So you might think, oh, you're adding pi to it, so why is it not going to third quadrant? Okay. That's because this is negative. Case 3. If C1 and C2 are negative. That is when both sine and cosine are negative, so we are in the third quadrant. The good thing is, if you do the same thing, it's going to work here as well. Okay, so phi is going to be, so you don't need to change anything. So phi is tan inverse of C2 over C1 plus pi. What's the difference between these two? Here, this term is going to be positive because both C1 and C2 are negative. Okay, so you're adding a number to 3.14 in the third quadrant. Okay. This was negative, so you're in the second quadrant. So even if it looks the same, these are doing two different things. And case 4, sorry to kind of go in a slightly wrong order here. Case 4, if what's the case that we did not discuss? C1 is positive and C2 is negative. And that means cosine is positive, sine is negative. So phi is in the fourth quadrant. And you can obtain the new angle by doing tan inverse of C2 over C1 plus 2 pi. Once again, this is a negative number. Okay, because C1 is, sorry, C2 is negative, so this is negative. We are adding a negative number to 2 pi. It's going to be less than 2 pi. We are in the fourth quadrant, not back in the first quadrant. Okay. So when you do the spring mass problems, you have to keep a whole bunch of information with you so that you don't have to memorize all these things. Okay. So you need to find the solution first, write it in the amplitude phase form. Okay, the only tricky part is to figure out where your angle phi is lying. Okay, and for that you need to look at your constant C1 and C2, and depending on its sign, you need to either add pi or 2 pi so that it lies in the appropriate quadrant. This is a small note. Since you're going to focus a lot on the C1 and C2, okay, you need to know what it means by saying they are negative. So sign convention. Remember that this is your equilibrium position. Anything that goes up is negative, down is positive. Okay. Towards gravity, away from gravity. So x of 0 and x prime of 0 will be negative if upwards, and positive if downwards. That is what really means by saying there is C1 and C2 being positive or negative. Okay. The phi for cases 2 and 3 are the same, but you are adding two different numbers there. Okay. Case 2, you're adding a negative number. In case 3, you're adding a positive number. That's why I kind of wrote it here. Okay. This is a negative number here. This is a positive number because both C1 and C2 are negative. Okay. So even if they look the same, they're going to give you two different answers. Did I answer your question? All right, so let's do some examples now. Yeah, I know it's a long derivation and discussion, so let's see how to do this in some actual examples. Any questions before I do that? Been clearing that window for a long time now. Okay, example. So pretty standard routine problems. Okay, there is nothing twisted in any of these. If you get used to one of these, you know, it's pretty standard stuff. So given that a force of 8 newtons displaces a spring by 2 meters. Question 1, find the value of K. So K is a spring constant. This N stands for newtons, okay? Not north newtons. And this is meters. Suppose the mass of 2 kilograms. 2 kilograms is hung from the spring. Find the displacement x of t if x of 0 equal to 1 and x prime of 0 equal to 1. Okay, so let's start with very simple things. Okay, let's keep both of them as positive, and then we will start playing around with it. So that's initial displacement and initial velocity, both of which are applied down, okay, towards gravity. And question 3, write the solution in the amplitude phase form. Now there is a small request. Okay, this adding of pi and 2 pi seems to be a very stressful experience for some students. You know, they take, for some reason, when some students get obsessed with it. Just take it easy. Okay, it's a very, very, very small part of a big problem. If you miss that pi or 2 pi, you may probably lose 1 point. Okay, so don't spend 45 minutes trying to figure out, oh, should I add a pi or a 2 pi, and try to, you know, scratch your head. Just from a time management point of view on quizzes and tests, I've seen a lot of students just sit down and try to overcomplicate this thing. All right. In general, you should be able to write the differential equation, solve it, okay, and give the solution in a sensible form. That is the most important thing. Whether adding the pi or 2 pi, if you make a mistake, and you shouldn't make mistakes, but if you get that wrong, it's not a big deal. Okay. All right, so let's start with the differential equation here. Well, first we define K. Okay, so using Hooke's law, K is the absolute value of the force on the spring divided by the displacement, which is given by the 2 meters there. That's equal to 8/2, which is 4. If you want units, that's going to be newtons per meter. All right, so there's nothing complicated there. So to find the displacement, we need to find the or write the differential equation and solve it. Okay, so part 2, the differential equation is mx double prime plus kx equal to 0. Not kx prime, kx. There is no damping here, so it's just the spring and the mass. The mass is given as 2, so it's going to be 2x double prime plus k, which you just solved there in part 1, 4x equal to 0. Okay. You can just divide throughout by 2, so you get x double prime plus 2x equal to 0. The characteristic equation is r squared plus 2, not 2r. Okay. Equal to 0. So r square is -2. R equal to plus or minus the square root of 2i. That is my natural frequency, square root of 2. So when it says find x of t, in its raw form, it's just x of t equal to c1 cosine of square root of 2t plus c2 sine of square root of 2t. Simple harmonic motion with the natural frequency of rho 2. Now we can find your C1 and C2 based on this set of initial values given there. X of 0 is equal to C1. Okay. Always when there is no damping, X of 0 and C1 are the same. And that's equal to even with damping. Okay. And that's equal to 1. Okay. Cosine of 0 is 1, sine of 0 is 0. And x prime of t equal to, don't forget to do chain rule here, so it's going to be negative root 2 c1 sine of root 2t plus root 2 c2 cosine of root 2t. That is the velocity in general, and you can plug in t equal to 0, x prime of 0 equal to square root of 2 c2. And that's also given as equal to 1. So C2 is 1 over square root of 2. Again, we are lucky here because both C1 and C2 are positive. Okay. So the answer to question number 2 or part number 2 is x of t equal to C1, which is 1 cosine of root 2t plus 1 over root 2 sine of root 2t. So if the question is not asking you to find the amplitude phase form, that's where you would stop. Okay. So up to here, it's pretty much what we were doing yesterday with 2.3, except that you're using different letters here, but same thing. All right, now let's do this amplitude phase form. Okay, so C1 is 1, C2 is 1 over root 2. So calculating the amplitude is pretty easy. So this is one of those parts where you might need to use a calculator to do some small calculations. Okay. All right, so the amplitude A is the square root of C1 square plus C2 square. That's the square root of 1 square plus 1 over root 2 square. That's going to be the square root of 3/2, right? Not particularly interested in what that is equal to in decimals, so just write the square root of 3/2, that's fine, the square root of 1.5. Okay. Both C1 and C2 are positive, so phi is in the first quadrant. Okay, so phi is tan inverse of C2 over C1. Okay. Both are positive, so it's going to be tan inverse of C1 is 1, so C2 is 1 over root 2. This is not 45 degrees. Okay. First of all, your calculator should be in radian mode because this is calculus. Okay. So can you tell me what phi in radians would be, not in degrees? Don't tell me things like 78.5 or so. Even your cell phone calculator should be able to do this. So just 0.62. Is that what you said? Don't forget that pi over 2 is 1.57. Anything less than that at least makes sense to us. That is in the first quadrant. Okay. So 0.62 is the value of phi. So this same thing in part 3 of this question would be x of t equal to square root of 3/2. The sine of omega is square root of 2. Okay, that doesn't change. It's a natural frequency. T minus 0.62. That's it. I know when you derive it, it looks like a big drama, but when you do the right calculations, it's pretty easy. Any questions on this? Yep. What? I don't know that equation. I always like to write the differential equation and solve it. The other one I don't know. Those are a lot of things for me to memorize. So just yeah, I mean, if you do the square root of k over m, you will get the same thing. That's right. Yeah. Fewer things to remember, the better. Any other conceptual or any other questions? So let me just make some small changes to the same problem and ask you to redo this. Okay. So example 2. Redo the same problem, which means everything up to this part is the same. Okay, I don't want to do a whole bunch of other problem with different numbers. Okay. So redo the same problem, but this time with x of 0 equal to -1 and x prime of 0 equal to 1. And example 3, redo the same problem with x of 0 equal to 1 and x prime of 0 equal to -1. Just to get some practice with this pi business. So you can kind of start from here. You don't have to go back and redo the whole problem. This solution is still the same. It's the values of C1 and C2 that is going to change. Even the amplitude is the same. All right, so if you change your x of 0 from 1 to -1, your C1 becomes -1. Okay. That does not change the value of C2 though. Okay. C2 is independent of C1 here. So the only change here is that this will be a negative because C1 is negative. C1 is negative, C2 is positive. Okay. So you need to go back and look at what really we wrote for this particular case. When C1 is negative, that means based on this right angle triangle. You shouldn't be changing this triangle around according to your whims and fancies. This should be kept the same so that you don't have to change your notes. Okay. So your C1 is negative means cosine is negative, sine is positive, and that's in the second quadrant. Okay. That means you have to add a pi so that you keep your phi in the second quadrant. So phi is going to be tan inverse of C2 over C1, which is 1 over square root of 2 divided by C1 is -1 plus pi, which is 3.14. You don't have to get obsessed with the next 100 digits of pi, just write 3.14. That's good. Okay. This should be a negative number now, right? So it's the same numerical value, 0.62 or whatever we wrote earlier. Okay. Yep. So this is going to be negative 0.62. So you're doing 3.14 minus 0.62. That's going to be 2.52. Amplitude is still the same. Frequency is still the same. This one is now going to change to 2.52. So if it was in the third quadrant, you would have added these two and obtained something that is more than pi. Okay, that's the only difference between quadrants 2 and 3. So what changes for the next notation of the problem? If x of 0 is 1 and x prime of 0 is -1, what is the only difference here? Yeah, C1 is positive, C2 is negative. Yeah. There are lots of numbers here, 2, 3, 2, 3. So this refers to the next one. That is this one. So x of 0 will be back to +1 because C1 is x of 0. X prime will give you C2 to be negative. Okay. So that will remove this negative and just transfer it to the second term. Okay, so that's all what's happening here, right? With the change in sign of the initial values, just C1 and C2 just keeps dancing back and forth. Okay. I think I'll have to avoid clutter. It's probably nice to just erase this and do it. Yeah. So I'm doing this case here. So C1 is 1 and C2 is -1 over √2. Okay, again, based on the same right angle triangle. C1 is positive, C2 is negative. That means because sine is positive, sine is negative. We are in quadrant 4. Okay. Which means it should be less than 2 pi or less than 6.28. Okay. So this is going to be phi equal to tan inverse of C2 over C1 plus 2 pi. Again, all measurements should be in radians so that it makes sense. You cannot add something like 275 degrees to 2 pi. Okay. Radians plus radians. And this is again negative 0.62 plus 6.28. Now that's a more complicated thing to subtract. What is it? 4, 3, 5. 5.34. 5.66. Okay, if you say so. Yeah, 8 minus 2 is 6. 5.66. Thank you. This is same, that is same. Okay. We are adding 2 pi because phi is in the 4th quadrant. So that's it. So don't get too obsessed with this phase angle phi. Okay, it is important, but that shouldn't be the key concept here. Any questions on this example? So you can generate millions of examples with more values of m and k, but the concept is the same. All right. If you don't have any questions, let's bring back our favorite dashpot back into the picture. The reason why I did not erase any of those in that section 2.3 stuff is because we need that here. Okay, so back to C not equal to 0. Okay, so now we have a full system but no external force. Okay. So this is your K, M, C. C is the damping coefficient, K is the spring constant, M is a mass. Okay. The governing differential equation with no external force would be mx double prime plus cx prime plus kx equal to 0. You don't have to memorize this. Okay? When you do a problem, just look at the notes or textbook and write it down carefully. Because sometimes students put the k here, c there, get all kinds of funny results. Before I start doing the mathematics of this, okay, let me ask you, where do we see this applied in real life? We don't really deal with spring and mass in homes. So there is a place where we use this every day, which probably may not know it, but living in a city like Boston, you should know it. Where is the Spring-mass-dashpot thing mostly used? It's not in a computer or in a cell phone or anything. You know. Scale. That's a good example, actually. But you know the kind of oscillations we are talking about. Yeah, I know the old one. I know. So, but the kind of oscillations we're talking about, it's a much bigger thing. Yeah. A car suspension. Okay, so the shock absorbers in a car. Don't tell me that you have never thought about it. Anytime you go into a pothole in Boston, okay, or anywhere, you are back in the same shape and not crooked like this because there are nice shock absorbers in your car. Okay. There's a huge spring there. It's not like the spring in your ballpoint pens. Okay. The springs in your cars are pretty big, and that's supposed to kind of dampen the oscillation. Instead of going to a pothole and kind of go dancing up and down, okay, you come back to equilibrium pretty soon. So that is the most common application of spring-mass-dashpot system. Okay. All right, so let's start solving it. So the characteristic equation is mr square plus cr plus k equal to 0. Okay. And please don't forget this truth that all these letters are strictly positive. That is important because without it we cannot analyze this problem carefully. So all those things are strictly positive. All right, so the roots of this equation are given by r equal to negative b, which is negative c, plus or minus square root of c square minus 4 mk, the whole thing divided by 2m. And for convenience reasons, I'm going to kind of write it as two separate terms. Okay, this is negative c over 2m plus or minus the square root of c square minus 4 mk over 2m. So if c was equal to 0, we are back to our earlier problem. Okay, this wouldn't be here. This will be back to square root of k over m. So if c is not equal to 0, you can see the term looks a lot more complicated now. So case 1, based on what I have written here, okay, if c square is greater than 4mk. So case 1. Remember that c is a damping coefficient. Okay. When you say c square is greater than 4mk, it's heavily damped. Okay. So this is called an overdamped oscillation. I'm going to put oscillation in quotes because actually there's no oscillation here. Okay. Overdamped. That's actually a misnomer. It's actually overdamped motion. Okay. Because you let it go, it comes to a stop almost immediately because the damping is so strong. Okay. So there's actually no oscillation. It's almost like you take a spring and mass and dip it in honey or something, it's hardly able to move. Okay. So there are two real but distinct roots here, R1 not equal to R2. R1 would be the positive root and R2 would be the negative root. Okay. Just for clear understanding, let me write those terms here explicitly. So R1 is negative c over 2m plus the square root of c square minus 4 mk. Remember that c square is greater than 4mk here. Okay. Divided by 2m, and R2 equal to negative c over 2m minus the square root of c square minus 4 mk over 2m. I'm going to make some wild claims here. Okay, I hope all of you will agree with me. I'm going to claim that this thing is always negative. Do you agree? Based on my sign convention that mass is positive, c is positive, k is positive. This is negative, that is negative. Two negative numbers added together is always negative. No doubts, right? I'm also going to claim that this is always negative. Now you're thinking, really? What do you think? Yeah.
It depends if c is greater than bracket c squared minus 4mk.
Well, c square is greater than 4mk. Okay, so there shouldn't be a doubt about what. Right. So c is positive, and c square is greater than 4mk. So I think your question was probably this: that what if this term comes out to be a stronger positive term than this? That won't happen because when you take c square, subtract something, and take the square root, Okay, it becomes smaller and smaller and smaller. Two things you're doing here. Subtract this, take the square root. Okay. By the time you're done with this is going to be a more dominating term. So this is negative, that is negative, always. Okay. So both R1 is negative and R2 is negative. Why do we care? Because we are trying to find what happens to the spring in course of time. Okay. Both these solutions are exponentially decaying with respect to time. There is no exponential growth here, otherwise the spring will break. Okay. So x of t equal to C1 e to the power of R1t plus C2 e to the power of R2 t, with R1 and R2 both being negative. Okay. That is what an overdamped oscillation means. There is no oscillation here, it's an exponential decay here. Okay. Both exponentially dies down. And that's a pretty good thing to do, to expect. If you don't want any oscillations, just kill the oscillations. Okay. So that is case number 1 here, except that I'm using x and t instead of y and x. All right, now let's look at the second case. If c square is equal to 4mk, now you're hitting the sweet spot. Okay. So there is this magic number where both those things are kind of balancing out. C square is equal to 4mk. It's called critically damped, again, oscillation within quotes. Okay. Again, there is no oscillation, because if you look at your case 2 solution, there is no sine or cosine terms there. Right? So it's critically damped because it's that break point where it transitions from case 1 to case 3. This is what you would ideally expect in your car. Okay. Just that sweet number where it balances out and there is nothing going on. Okay. It's a very strong case now. So this is case 2. So you have R1 equal to R2. Equal to negative C over 2m. Okay. C is a damping coefficient. So we have an exponentially decaying term because of the damping. Okay. So we have x of t equal to C1 e to the power of negative C over 2m times t plus C2 t, not x. Okay, you're writing x as the dependent variable here. So you're multiplying a t to get rid of the repeated root. So C2t times c to the power of negative c over 2m times t. So as t goes to infinity, both these terms are still going to 0. Okay, but this thing is a much more stronger killing than the first one. Okay. Because as soon as the oscillation starts, it stops. Okay. This one, as you take the limiting case, you have to use L'Hopital's rule and all that stuff. Okay. But this is a very strong case, and that is the most ideal situation in your car shock absorbers, where you go into a pothole and you come back up. So no unnecessary up and down oscillations. So both cases, cases 1 and 2, there are no oscillations, which means you don't have to worry about things like amplitude, phase form, and all that stuff, because case 1 is exponential, case 2 is also exponential. Okay. So there is no oscillation or amplitude phase form. For cases 1 and 2. That's good news. You don't have to worry about this phi thing. Okay. Now, case 3 is where all the beautiful things happen. Okay. You have exponential and these oscillations. That is where the pictures get more nice and wavy. Okay. So case 3 is if c square is less than 4mk. So there is damping, but it's not enough, right? It's called underdamped oscillations. Now there is oscillation, okay, because based on 2.3 there are these cosine and sine terms, so it has to have some kind of a wavy pattern. It's underdamped because it's not enough to kill it fast enough. It also means we have some imaginary roots. Okay, so your R1 and R2 would be of the form P plus IQ and P minus IQ. The same pattern for P and Q as I wrote earlier. Okay, I'm not going to repeat that thing. So for each problem, you'll have a P term and a Q term after you solve the quadratic. So your P is going to look like this, and Q is going to look like this. But the 4mk and the c square are switched because you have an I multiplying it. Okay. So the solution would be solution to case 3, which is underdamped oscillation would be x of t equal to e to the power of pt. Remember that p is negative, okay, because c square is less than 4mk, and your p is this term here, negative c over 2m. That's always negative. Okay. So that is a damping term times c1 cosine of qt plus c2 sine of qt, where p is negative c over 2m is called the damping factor. Once again, if c is equal to 0, it's simple harmonic motion. Okay. So c not equal to 0 is creating this slowly dying oscillations. Q is a special kind of frequency. It's not a natural frequency anymore. Okay. Q is called the false frequency, also called the pseudo frequency. Why is it called pseudo frequency? Because it is corrupted by your damping term. Okay. This is your natural frequency. You need to understand these two as two different frequencies. Okay. This is when C is equal to 0. It's called the natural frequency. Once you put C back into the picture, it is no longer its natural frequency, it is kind of messed up. Okay. And that messed up term is given by this complicated looking stuff here. So Q is given by the square root of 4mk minus c square divided by 2m. For those of you who are not very convinced, you could put c equal to 0 in here, and you will see that this will simplify to the square root of k over m always. Okay. So this is the case with c not equal to 0, it's called the pseudo frequency. In c equal to 0, you have the natural frequency. Okay. So there is no omega equal to square root of k over m when c is not equal to 0. That is one thing that I have found it very difficult to convince students about. For some reason, students keep on writing omega with a damped oscillation. Okay, there is no such thing. The damping will kill the natural frequency and create this slightly slower frequency. Okay, so you have to account for that fact. So I'm going to erase this now that I have used it. So the amplitude phase form for case 3 for underdamped oscillations will be x of t equal to e to the power of pt times a cosine of qt minus phi. Okay, not omega here. So this e to the power of pt is still here because that is the damping term, otherwise it will be simple harmonic motion. Okay. A is amplitude, same thing, square root of c1 square plus c2 square. And phi is also the same business. Those of you who are paying attention, please pay attention to this part, okay, not omega. There is no natural frequency in this case. It's, I don't know, I don't know what exactly goes wrong when students copy it from one place to the other. A lot of students just write it as A cosine of omega t minus phi for this particular case. It's not, okay, it's Q. All right, so if you keep those things in mind, it's pretty routine calculation. All right, let's do an example, and I think we have enough time to just do one of them. Any questions about any of these? Yeah. Because they are not oscillatory, they are the exponential functions, right? The amplitude phase form is only for a wave. The other one is just exponentially decaying things. Any other questions? Okay. All right, so then let's do this example. Consider a system with m equal to 1. C equal to 6 and k equal to 13. Okay, just trying to make up some nice numbers here. So these are the same numbers we used in one of our examples yesterday. Okay, so sorry for the repetition. And let x of 0 equal to 1, x prime of 0 equal to -1. Okay, now that we are used to all the sign conventions, we could use both. Find x of t and write in the amplitude phase form. It's, I hope, gives you enough hint that this is case 3, because I won't ask you this for cases 1 and 2. So we are expecting an underdamped oscillation. All right, so the governing differential equation is mx double prime cx prime plus kx equal to 0, which is x double prime plus 6 x prime plus 13x equal to 0. And the characteristic equation, see, we did this yesterday, right? R squared plus 6r plus 13 equal to 0. So R would be negative b plus or minus square root of b square minus 4 times 13 is 52 by 2a is 2. Negative 6 plus or minus the square root of negative 16, which is 4i over 2, which is negative 3 plus or minus 2i. So the damping term is negative 3, and the pseudo frequency, not the natural frequency, is 2. So the general solution is x of t equal to e to the power of negative 3t times c1 cosine of 2t plus c2 sine of 2t. Now starts some slightly time consuming things. Okay, when you do this initial values, you will see it, you write out a lot of things. And anybody up to there? Okay, any questions? All right, so x of 0 is 1. So if you plug in your t equal to 0 there, you get C1 equal to 1. That's the easy one. Right? Now you have to find the derivative of this, which involves product rule. Okay. So x prime of t, the derivative of e to the negative 3t is negative 3 e to the negative 3t times the entire term cosine 2t e2 sine of 2t plus the first term times the derivative of the second term, which is negative 2c1 sine of 2t plus 2c2 cosine of 2t. This looks pretty lengthy when you write it, but it's actually nothing complicated if you know the product rule. And we are going to plug in t equal to 0. So x prime of 0 is going to be, well, sine of 0 is 0 anyway. So we have c1, so actually negative 3c1 plus 2c2. So with the case with damping, your C2 is not exactly x prime. C2 is slightly more complicated than what we used to have for simple harmonic motion. This is given equal to negative 1. But you know that C1 is 1. So we have 2C2 equal to 2. Okay, if you bring this over here, so it gives you C1 equal to 1. So C2 equal to 1. That was not planned. It somehow came out to be both C1 and C2 equal to 1. So both are positive. I was planning on one of them to be negative, but oh well. Both of them are positive, so lucky day. So our solution to question number 1 is e to the power of, don't miss this term, okay, this is a damping term. So e to the power of negative 3t times cosine 2t plus sine 2t. Okay. Now we need to do the amplitude phase form. So for question number or part number 2, amplitude is the square root of c1 square plus c2 square, square root of 1 plus 1, square root of 2. And phi, actually, you could tell me that value without calculator, right? It's just pi over 4, not 45 degrees, pi over 4. Tan inverse of C2 over C1. That's, if you don't know pi over 4, you could use a calculator and get it as 0.7, whatever it is. So when you write the amplitude phase form, please make sure that you don't miss this term. It's still oscillatory and exponentially decreasing. So it's e to the power of negative 3t equal to times the square root of 2, its amplitude, times cosine of, I know you're tempted to find the natural frequency. No, q is 2. Okay. 2t minus phi, which is pi over 4. Okay. So that is the exponential term. This is the amplitude here. That is the q term, okay, which is 2 minus phi. So this 2 is q, the pseudo frequency. So I should have annotated back here. All right, any questions? So you can see once you get used to 2.3, 2.4 is a piece of cake almost. Can you quickly do this one? C equal to 4, K equal to 4. No. Oh, yeah. 1, 1, 4, and 4. 1 and negative 1. Is the system over, under, or critically damped? And find the displacement x of t. Okay. For some reason, I'm not going to ask you to write this in amplitude phase form. I don't know why. Maybe I'm in a nice mood. Okay. Can you quickly do that? And that will be it for today. So tomorrow we'll start non-homogeneous equations. What is your expert opinion on the first one? Over, under, or critically damped? Critically damped. Okay, c square is equal to 4mk. And for some reason, I left this here. Okay, case 2. So it's a double root of -2. So anything wrong in what I've written? It's a slightly annoying mistake that happens all the time. Yeah, this should be a t. Okay, unless if you're really obsessed with using y and x, you should write everything as y and x. Okay, you're writing x as a function of t, so this must be a t here, so that your solution does not look awkward. Okay. But I've stopped taking points off for that. I mean, I've seen it so many times now that gotten used to it. But try to be consistent with your notations. So x of 0 equal to 1. So that will be C1. So since it's critically damped, there is no amplitude phase form. And x prime, we need a little bit of product rule there, not too heavy. That's going to be -2 C1 e to the power of -2t. Product rule on this will give you plus C2 e to the -2t minus 2 C2 t e to the -2t. I do right. And x prime of 0 would be -2 C1 plus C2. Okay, this will be 0. That's equal to -1. But C1 was 1, so C2 is again 1. Cannot stop getting ones. So that's it. Okay, so there is nothing much to do here. So your final answer is x of t equal to e to the power of negative 2t plus t e to the power of negative 2t. All right. So I think it's going to be a nice day today. Don't let this dampen your mood. Okay. All right. Nice day.